physical process. Okay. After that, we will discuss to something related to the state of the material appear in the reaction, or sometimes in the real life, like a solution, discuss on the solubility, and then we will see some kind of the reaction you can see in the laboratories, or even in the natures, precipitation reaction, acid-base reaction, redox reactions. Okay, and then there are some information when you work with a solution and the quantitative analysis. Okay, so there are it's a lot of tasks we have to discuss, but it's not so difficult like when Fong introduced you about the molecular orbitals, for examples, right? Okay, so let's move to the evidence of the chemical reactions. Okay, so normally chemical reactions, as you know, maybe from the very first lectures, there are several types of the process happen in natures, right? The chemical process or physical process. So physical process will not involve any change in the materials, okay, or in the molecule of the inside the process, okay. But in case of the chemical reaction, you will see the changing of the molecule, okay. So when the molecule change, it means that you will get a new kind of matter or new kind of materials, okay. So they will let you to some evidence, give you an ability or chance to realize this one is a chemical process. For example, you will see the color change. It's like this, okay. You use the yellow colors solution, put into another solution, and it changes colors. So it changes color is show you the information that the molecule now is changing, and changing of its absorption of the visible light. Okay, so by that way you will see the change of the colors. Of course, the change of the color is not always the chemical reactions, like you see in the process where you dissolve some transition metal into the solution, like a cobalt 2 plus we discussed in several last lectures, right? When you put the cobalt 2 plus salt in the water to make a solution, it's become pink. The color is pink. But if you add some more of the if you put them into the how to say ammonia solution, okay, the cobalt 2 plus now is not change of its oscillation state, but a new complex generated. And in turn, actually it's quite hard to say that it's not this is a physical process or chemical process. We can see it's a chemical process too. Sorry about that evidence. It's okay, never mind. Another kind of the evidence is the gas formation. Of course, you see the gas formation mean you need to generate a molecule that can provide, that cannot be dissolved in a solution firstly, and this one will go out from the solution as a bubble, and by that way you will see the gas formation. Okay, the solid formation is another evidence in which you see if you put some transparent solution together, maybe the precipitate like this one, okay, or some solid will appear and precipitate in the bottom of the container. So this one is an evidence for chemical reactions. Okay, another is the emission of light. The emission of light here is show that you will need to generate a new molecule that can absorb and emit light. Okay, to generate the the luminescence phenomenon. Okay, and the last one is the process of the emission and absorption of heat. Okay, this one you will study quite carefully in the next semester for the general chemistry too. Okay, so it's this one you know very clear because you use it at home every day, right, to cook the food. Okay, but the very funny thing here, as I said to you about the very first in the very first part, that the evidence here can help you to realize is this one a chemical reactions, but sometimes it's not really. Okay, especially for the case of emission of light. Even we can imagine the emission of light. Emission of light is you need to generate a molecule that can absorb light. Okay, absorb light and then excite to the higher state, and then if the electron in the higher state they stay there and go back to the normal state, okay, they emit a light because this is a luminescence process. And you see this one, okay, this may be a chemical change because you need to modify, you need to prepare a new molecule with that properties. Okay, but sometimes, especially for the case of nanotechnology at this moment, we can find a lot of different things. Okay, like the case of the cadmium selenide or cadmium or C cadmium telluride. Okay, this type of quantum dot can show the luminescence process when they have a different size in the nanometer. Okay, as you see from 2 nanometer to 8 nanometer, the colors of the luminescence process for cadmium selenide is totally changed from blue to red. Okay, some other examples you can see very easy in the laboratories, like if you can go to 707 in USDH, you see the gold nanoparticles will have something similar properties. If we control the size of the gold nanoparticles from 20 to around 100 nanometer, the colors of that solution will totally change. But of course, this material is not changed, right? It's the gold, like the case of it's only cadmium selenide here. Okay, so the emission of light, or even the other, sometimes it's not really a process of changing of the changing the chemical properties. Okay, so the second topic related to the aqueous solution and solubility. Okay, so this one is the actually is not especially focused on the aqueous solution, but let's understand what is a solution firstly. Okay, and the components of a solution. Okay, a solution is a homogeneous mixture of 2 or more substances. Okay, it's a homogeneous mixture. Okay, you study about mixture in the very first lectures, right? So homogeneous mixture is mean that after you mix them together, you cannot realize 2 components inside, 2 or more components inside. Okay, this looks like the case you dissolve some sodium chloride. Okay, the common salt used at home, or sugars, into water. Okay, so in that case, you will start with a transparent water. After you put some sugar there, you mix them, you stir them, and then you get a transparent solution too. Okay, you cannot realize by color, by your eyes, that this one is a pure water, this one is sugar water. You cannot do this. Okay, in that case, we call sugar and water is a solution. Okay, so in that solution, you have some components, of course, right? So the guy is dissolved in the solvents. We call it solute. Okay, so in terms of sugar water, you get sugars is the solute. Okay, and the guy can do the dissolving. Okay, or the guy is the make the environments to dissolve the solute. We call it the solvents. Okay, so sugar water will be solvent. Okay. And of course, in the case of the solution, solvent normally will be the guy will present in the greatest quantity. Okay, you use a lot of water to dissolve the sugars or sodium chloride. Okay, much more than the solute. So the solution can be prepared with many types of solvents. Okay, if you use the solvents, is water, we call this one is the aqueous solution. Okay, but if you use some other solvents like acetone, okay, like ethanol, like dichloromethane, okay, some other kind of organic solvents, you cannot call it the aqueous solution anymore. Okay, so the aqueous solution or aqueous, sometimes you see the word aqueous next to the components in a reaction. This means that your reaction is happen in water. Okay. So okay. One properties of the solution. Okay, one property of the solution. Of course, the solution have a lot of properties. Okay, but one property of the solution is quite funny and important is the electrolytic properties. Okay, electrolytic property is mean the substance when they dissolve in the solution. Okay, this one will generate ions. Okay, substance in the solution will generate ions, or we can say the solution will contain ions at that moment. Okay, so the thing have you to realize the solution have an electrolytic properties or not will related to an ability of that solution to conduct electricity. Okay, so this look like here. If this one work like a wire, okay, if the solution there work like a wire, you connect the white, okay, the electric here, and two of the electrode will be deep in the solution. And if you see the circuits become closed, this means that that solution can conduct electricity. Okay, so now it depends the ability of the solvent, of the solution to conduct electricity. Now you can separate them into several things. Okay, the non-electrolyte is this one. Okay, in which you see the substance when you dissolve in the water or in any other kind of solvent cannot form ions. Okay, so by that way, the solution cannot conduct electricity and the circuits will not be closed. Okay, so there are no ions in non-electrolyte materials. Okay, in the other side, you will have another kind of solution can let the electricity move through, but it's not total electricity can move through. Okay, so in that one we can imagine there are only few ions generated when you dissolve that substance in the solution. Okay, so we call this one a kind of the weak electrolyte. And in the other part, if you see you dissolve a substance in a solution and the circuit and the electric can pass over this solution very simple, very easy. Okay, so you see the bulb here is lighter than this one. Okay, this one can be called a strong electrolyte. Okay. Oops. Okay, sorry, because of wrong activities. This one is called weak electrolyte, and this one is strong electrolyte. So, okay. So how can a substance can form electrolyte, can form the electrolytic properties, or can form ion in the solution? Let's see the process. Okay, this one is namely the dissolution in water. Okay, firstly, you need to know how a substance dissolves in the solution. Okay, for example, this one is in the process of sodium chloride and any compounds, you dissolve them in water. Okay, it's like when you cook some soup at home, you put some common salt there. Okay, so the process will happen by the bulk of the sodium chloride, like this. Okay, because of, you see, you may remember that sodium chloride and ionic compounds, so they appear as the crystal. Okay, with the negative charge and positive charge, they stay in order together. Okay, very close and order together. So when you put them into water environments, they will be surrounded by water molecule. Okay, water molecule. And in another part, let's understand water molecule: oxygen, hydrogen, hydrogen. Okay, oxygen have a higher electronegativity compared to hydrogen, so the oxygen will contain or bearing the negative part or negative charge, and hydrogen will bearing positive charge. Okay, so now you see there will be interactions between the water molecule with the negative positive dipole. Okay, with the negative charge and positive charge appear in the sodium chloride crystal. Okay, so you can see the part of negative charge appear on oxygens will prefer to attract the positive charge of the sodium chloride or sodium ions. Okay, so when they surround it like this, and when they strong enough, all the numbers of water molecule is high enough. Okay, is high enough. Now the interaction between the sodium and chloride will be weak enough to let the sodium ion go out from the crystal. Okay, so this is the process of the dissolving, and the similar thing will happen for the chloride minus ions. Okay, the chloride minus will be surrounded by the positive part of the water, okay, or hydrogens of water. So hydrogen will go closer and attract by the electrostatic force to the chloride minus, and then when the numbers of water molecule is high enough, they will let the bond between the chloride and the sodium in the crystal weak enough to let the chloride go out. Okay, so that process is we call the dissolution. Okay, and the process of water or solvent surround ions in the solution, we call it the solvation process, or we call another word is this ion as solvate. Okay, okay, so in normal way, the process of dissolving water, dissolving sodium chloride in water will be right like this: sodium chloride, solid form, okay, put into the water, it's become sodium plus AQ. Okay, this means that sodium plus now stay in the solution of with water, okay, with water as solvents, and it's be surrounded by water molecule, or it's be solvate. Okay, and another part is chloride AQ. Okay, so similar things happen. Chloride is solvate by solvents. Okay, in another side, when you take a look on methanol or ethanol, okay, you put into water. Have you ever drink some alcohol at home, guys? Have you ever been drunk? No. Okay, it's good. Yes. How do you feel when you're drunk?
Tired.
Higher. Okay. Okay, it's look good. Actually, the how to say the phenomenon of the feeling when you're drunk, you feel higher, right? Actually, I am normally take that examples for the process of one molecule stay in the ground state. Okay, is the accept or is gain some energy from light, for example, and move to the excited state. Okay, you see, it's totally right. It's totally the same when you're drunk. Okay, you add some alcohol into the body, you feel high, but the higher state there is not stay permanently, stay with the long time, right? Just after one day, for example, you move back to the ground state. And it's similar to the case of the molecules stay in the excited state. They cannot stay there for a long time. They will go back to the ground state and emit some light. Okay, emit some other thing. It's maybe light, it's maybe heat. It's look like after you drunk, you always want to talk something, right? Okay, it's another examples. But I have an advice to you. So let's try to drunk at least 1 or 2 times. Okay, it's become important because of you should know exactly how much of the alcohol you can drink. Okay, this when will be very, very important in the futures when you have to do some communication and cannot avoid alcohol. You should know exactly that you how much of alcohol, of beer, of alcohol, of wine you can drink. Okay, especially for girls. Okay, so let's go back to the lectures. Okay, so this solution in the water, the last one is the sodium chloride, an ionic compounds. Okay, and the ionic compounds normally can generate an electrolyte or generate ions and become an electrolyte in the solution. Okay, but in this case, when you put some methanol, some ethanol, or some acetone, okay, in water, they are molecular compounds. Okay, the molecular compound when it is dissolved in the water, okay, this one cannot form ions. Okay, methanol CH3OH. Okay, or ethanol C2H5OH, or acetone CH3COCH3. Okay, this one dissolve because of the hydrogen bonds or hydrogen interaction with water. Okay, the molecules of methanol, of ethanol, of acetone in water still keep the same. Okay, they cannot generate, they cannot they cannot separate or cannot be solved in the water. Okay, so by that way you can form ions, and then they lead you to a property that this one cannot conduct electric. Okay, so normally the molecular compound when you put in water this will be bearing the non-electrolytic properties. Okay, so let's separate the strong and weak electrolyte. Okay, for non-electrolytes, it's nothing to say because of this one is dissolved but cannot form ion. Okay, now electrolyte can be separated into strong and weak. Okay, so strong electrolyte is mean that 100% of the substance will be dissolved and then separate into the ions. Okay, this means 100% of the molecule dissolved in water, okay, will be solved and appear as the ions. Okay, so the strong electrolyte normally they including the soluble ionic compounds like sodium chloride as the example before. Okay, some strong acid and strong base. the guy is very easy to form the hydrogens or the protons in the aqueous solution. Okay, so this one is 100% dissolved in the solution as iron. Okay, for the case of weak electrolyte is partially ionized in solution. Okay, so it means that only a part of that substance, of that molecule, will dissolve in the it's not dissolved. Let me say it again. The weak electrolyte will be only a part of them be ionized in the solution. Okay, so this means that when you dissolve some weak electrolyte like this one, acetic acid, in the solution, you will form all of them. You will still have some of the acetic acid. Okay, you also see some acetate ions and protons in that solution. Okay, but in the case of strong electrolyte, you will see only protons and sodium and chloride minus in aqueous solution. Okay, so strong electrolyte, weak electrolyte is different because of the amount of the substance can be ionized in the solution. Okay, for the case of weak electrolyte, normally you will see it appear in weak acid and weak base. Okay, it's sometimes some acid, some organic acid. Most of them is organic acid and organic base. Okay. So actually, this one is the example we see before, right? But now you have a three of electrolyte, including the non-electrolyte, weak electrolyte, strong electrolyte, and you have to separate, classify this part into each type. Okay. Now very simple. You see sodium chloride is strong base. Okay, this is strong base. So strong base can be dissolved very easy and be ionized very easy in the solution. So strong base will be strong electrolyte. Okay, you have a carbonic acid. Carbonic acid, as you know from high school, this one is very weak acid. Okay, so weak acid, it should be weak electrolyte. Okay, and the last one, you have a methanol. As we discussed before, methanol is a molecular compound. Molecular compound cannot generate ions in the solution. So this one is non-electrolyte. Okay, very simple. So for the solution, the parameter, the most important parameter of any kind of solute in the solution is the solubility. Okay, the solubility will give you an ability to dissolve of that substance in water. Okay, if you have some materials or some molecule can readily dissolve in water because it is solute materials or solute molecule. Okay, solute matter. In the opposite side, it will be insolute materials. Okay, so for the case of solubility, you have a solubility rule, like in the table you see after. Okay, in the lower part. So it depends on the type of the ionic compounds. Okay, depend on the type of ions appear in that molecules. This one is solute or not solute. Okay, for example, some guy like the alkaline ions, lithium, sodium, potassium, okay, or ammonium. This one is solute, very easy to be solute. Okay, but some other kind, like the phosphate, like carbonate, okay, or sulfite. Okay, most of the ions, anion here, when they combine with the metals to form a salt, for example, okay, most of them cannot dissolve in water. You see the calcium carbonate stay in the nature, very stable. Okay, you see some of the hydroxy phosphate or apatite. Okay, we have an apatite mine in the on Lào province, a very big apatite mine there, and because of it, it's insoluble, so this can stay in the nature, right? So based on the tables here, you can define which one is soluble, which one is non-soluble. Okay, this one is what were introduced to you in high school as well. Okay, so let's summarize the part of solubility and electrolyte concept. Okay, the soluble substance, when they dissolve in water, when one thing dissolves in water, it can generate ion or not. Okay, so it can be electrolyte or non-electrolyte. Okay, for the soluble ionic substance, most of them will be the strong electrolyte. Okay, very simple. Soluble molecular substance, normally non-electrolyte, and sometimes it's weak electrolyte. Okay, and just only few molecular substance, like the case of sodium of the hydrochloric acid, a strong electrolyte. Okay, so there's some conclusion for you to remember is a part of the solution, solubility and electrolyte concept. Okay. So do you have any question for the first part? No?
No, sir.
Yeah, it's very simple from high school, right?
Yeah.
Can you go back to the last slide for a while?
The last slide?
Yeah, thank you.
Okay. So, do you want to ask something?
Not at the moment.
Or you just need it for
I
take a
think he's
picture?
taking note.
Okay,
Yeah.
got it. Thank you. So, now you know that chemical reaction happen a lot in nature. It's okay. So we can classify them, of course. Actually, you see, Phong is writing here only two types of the reaction: acid-base reaction and oxidation reduction reaction. Okay, so maybe in high school you will see that you will have some other reaction like kind of how to say exchanging reaction. You have some kind of combustion reaction. You have some kind of precipitation reaction, something like that. Yeah, what's happened? No. Okay, so actually in term of the how to say of the modern chemistry, okay, especially after you study about the Lewis acid base theory, we can classify almost of the reaction without the change of the oxidation state is an acid base reaction. Okay, Mr. Hein, right? Okay, he's turned it off. Thank you. Okay, so it means that after Lewis acid-base theory, you will study, we can separate almost of the kind of the reaction without the change of the oxidation state is acid-base reaction. Okay, and then because of the first part cannot contain the change of the oxidation state of the compounds of the elements. Okay, so the second type of the reactions of chemical reaction will be named the oxidation reduction reactions, or we can write this one redox reaction. Okay, So in the last part, in the part of the redox reaction, I will show you some video of some funny thing we can record in the laboratories. Okay. So oxidation reduction reaction normally involve the transfer of electrons, and by that the oxidation state of the elements will be changed. Okay, so we'll see it after. So the very first type of the reactions, you see it very simple or very common, is a precipitation reaction. Okay. So the precipitation reaction is a process when you have a aqueous solution of different ionic compounds. Okay, when you pour them together, you will see some of the solid appear. Okay, so it looks like a process we see a solid precipitated. Okay, so in that reactions, you will see some new material cannot be dissolved in the solution anymore. Okay, and it's moved out as a solid, and normally it's crystal. Normally, I'm not saying all the time, but it's normally crystal, especially for the case of the ionic compounds. Okay, so for example, when you take a solution of magnesium chloride, this one is transparent, okay, colorless transparent, and silver nitrate, this one is colorless and transparent too. Okay, it looks like exactly the same with water. And then when you put them together, you pour them together. This one aqueous, and after that you will see the white precipitate appears here. Okay, because of the silver chloride cannot be dissolved in water. Okay, we can define the solubility of this one in the tables of solubility in the last several slides. Okay, so this one is the explanation on the precipitation. Actually, it's a description for the precipitation reaction. So it means that if you can prepare a mixture of solution, okay, a mixture of the different solution in which two kinds of ions can generate an ionic compound that cannot dissolve in water, in solvents. Now you will get a precipitation reaction. Okay, it can be sodium chloride, it can be barium sulfate. Okay, very famous in high school. Okay. So for the very first, I would say very first comments. Okay, very first understand on the insoluble materials. Okay, at this moment, let's understand any substance with a solubility smaller than 0.01 mole per liter, okay, can be considered as an insoluble materials. Okay, insoluble materials. So actually, it's not totally right, because we call this one is the how to say less solute materials. Okay, it's not really insoluble materials. With the insoluble materials, you will see the concentration of the ions appear from that material in solution is normally 10 power minus 7, 10 power minus 6 mole per liter, something like that. Okay, but at this moment, let's consider the guy can provide a concentration in the solution smaller than 0.01 mole per liter is insoluble material. Okay, so for the reaction of precipitation, okay, you have to predict. Okay, so as the last slide I said, if you can find a pair of ions that can combine together and form an insoluble materials, okay, the precipitate form. Okay, so how can you do that? We can do in several steps like this. Well, firstly, note the ion present in the reactants. Okay, note the ion present in the reaction. So let's take a look on the examples. Okay, note the ion present in the reactant. This means that you have to separate this compound into ions. Okay, so now you will have the ion of magnesium 2 plus. Okay, the other ions of this compound is nitrate minus. Okay, the other ions generated from the other compounds will be sodium plus. Okay, and the last one will be hydroxyl. Okay, so they are all the ions appear in the system. Okay, so let's remember, write AQ in this one. Okay, let's continue for the other. So now you have to move to the second part. Consider the possible combination of the cation and anion. Okay, so cations, you have a magnesium and sodium. Okay, anion, you will have a nitrate and hydroxyl. Okay, so when you combine this one with this one, you will have the reactants, and the reactant is dissolved in water, so it's not insoluble. If you combine magnesium and OH minus, this one will form a materials magnesium hydroxide, sorry. Okay, and this hydroxide precipitate. Okay, so you can be sure, or you can confirm this materials is insoluble based on the solubility tables, right? Another kind of the combination related to the cation of sodium plus. Okay, but in the solubility table, you will see the sodium plus will form all the kind of salt with any other anions is soluble materials. Okay, so sodium plus, we don't need to care about them. So it means that this reaction will form magnesium hydroxide precipitate. Okay, so now we can write this reaction easy. MgOH2 solid, okay, and sodium nitrate. Okay, this one is AQ. So this one is the reaction. Okay, this one is a reaction of the precipitation. So another examples is a mixing of the lead nitrate, PbNO3 2 times, and sodium chloride. Okay, so the process is quite similar to the last part when magnesium OH generated. Okay, this one will be generate this guy. I will write it higher. It's okay, move it out. PbE2 solid. Okay, so the process happened like you put Pb nitrate, dissolve in aqueous solution, okay, with sodium iodide, okay, and then you will generate a solid of the lead iodide. Okay, the lead iodide will appear in the very first state is the lead ions and iodine ions, okay, and they combine together and form a seed, a very small seed, okay, just several ions. After that, the seed will grow, okay, and form a kind of ionic compounds as a crystal, like you see in this part. Okay, this one is stay in the order together and form crystal. And when you have a big crystal enough, okay, when the crystal is growing to the bigger size, and when they reach to the big enough, they will become insoluble, or you will see some solid in that solution. Okay, and they go deep into They go deeper into the bottom. Okay. Okay. Oh, sorry. There are some of the troubles. For a second, please. I give you another. So this one is look better. Okay. So why we put some why we put this the examples of PBI2 as the precipitation reaction to you in the last one, because of PBI2, you see very funny materials, and we can use the crystal of PBI2 or lead iodide to prepare a kind of material we call the perovskite. Okay, very simple reaction. You put the crystal of PBI2 in a solution of this one, for example, okay, methyl ammonium iodide, and then you will get a kind of material like the case of we call ABX3. Okay, this structure is namely perovskite. Okay, so do you see here that we can control very easy the part of A, also B, okay, also X here, okay, in the structures, and they generate a crystal, something like that, and you see B and X will form a kind of octahedrons, and they block A inside, okay, a very big pore inside, and A will block there, okay. The perovskite become very interesting material because of this one is a kind of the semiconductors. So we are researching on perovskite to use as the solar cell, okay, as the solar cell. So you see, there are some of the technique when we use the silicon solar cell, okay, when you go to some of the province in the middle of Vietnam, like Bình Định province or Ninh Thuận province, you see some of the solar cell field, okay, in which they generate the electric from the solar light, okay, and all of that field is based on the technology of using silicons, okay, all the semiconductor there is silicons, but you can see the growing of the silicon technologies and the perovskite technology is totally different, right? Perovskite is going much faster compared to the very first one. Okay. One of the trouble of perovskite is not stable. Okay. So a lot of research still on that direction to improve the stability of the perovskite. Okay. So for the precipitation reactions, let's separate them into the molecular and ionic equation. Okay, the last reaction we are writing down in the all of the last slide, we name them is a molecular equation. Okay, in the molecular equation, you will show the complete chemical formulas of reactants products. Okay, it means that you show the compound there. Okay, you show all the compound there. Okay, in another side, you will prepare the complete ionic equation in which you have to show all the strong electrolyte as an ion. Okay. So in this kind of the reaction, you will get all the kind of ions firstly, and sometimes some other substance. Okay, some other substance. For example, the non-electrolyte materials okay, molecules, weak electrolyte molecules, because of they appear in the solution as compounds, not ion anymore, right? So, for example, from this reaction, you know the barium sulfate is a precipitate, okay? So when you write down this reaction is a complete ionic equation, you will start with the ion generated in the solution of the reactants, okay? And then you write down the ion can appear in the products like sodium plus and hydroxide minus, right? And you write down the guy is the barium sulfate because of this one is a solid, it's not dissolved, it cannot generate ion anymore. Okay, let's write down them as barium sulfate. Okay, and as you see, for the complete ionic equation, the sodium is appear here. Okay, hydroxide appear here, and you see also the sodium appear in the products, and hydroxide appear in the products. So what should you do? Very simple. If you have that ion on the left side and also that ion in the right side, okay, this means that it's not important, this reaction, right? So let's cancel that. And after cancel them, you will get another kind of reaction we call net ionic equation. Okay, the net ionic equation is mean this kind of reaction will show only the reacting species in the chemical equation. Okay, it's only barium 2 plus and sulfate 2 plus 2 minus, sorry, to form the barium sulfate. Okay, and you get this one. Okay, net ionic equation. So normally, two common reaction kind of reaction of the two common kind of equation you see is the molecular equation and net ionic equation. Okay, the complete ionic equation is just for you to define the net ionic equation from the molecular equation. Okay, it's not really important. Okay, so actually you see the process of writing a net ionic equation as I write before. Okay, so can we skip this? Okay, so Tom is very carefully, and he give you examples of step by step. Okay, the first step related to molecular equation. Okay, so this form. Sorry, there is some trouble when I modified the PDF file to the PPT. So this step can be generated by the molecular equation in which you exchange the cations or anions. Okay, so in which you will get the compound of silver SO4, okay, and sodium nitrate, number 2 here. So you get a balanced equation. Okay, so the thing is that you have to define the state of the compounds, okay, and compare to the solubility tables. We can define that silver sulfate is a solid, okay, insoluble materials, and this one is solute materials. Okay, so this one is after this finish the first step. Okay, so now you know in this reaction is silver is prepared or is produced the silver sulfate as insoluble materials. Okay, firstly. Okay, so it's what we did in the last time. It's the solubility table. Okay, and then in the second step, let's write down. Can you imagine it? Sorry, because of there's some trouble when in the technical part. So in step 2, actually you are writing down the complete ionic equation, right? So in this one, you have to write down all the kind of ion can appear in both reactants and the products. Okay, so you start with silver nitrate. They prepare the silver ions, nitrate ions, and another reactant including sodium and sulfate. Okay, the products will be the sodium. Okay, it dissolved because of all the kind of sodium salt dissolved. Okay, all the kind of nitrate salt is soluble or dissolved. So nitrates stay as aqueous. Okay, and silver sulfate stay as a solid or precipitate. Okay, so after you get the complete ionic equation, the work now is to cancel the same ions or spectators. The guy cannot be involved in the process. Okay, so you have a sodium and nitrate, sodium nitrate, sorry, nitrate sodium, and then the net ionic reactions will be silver plus sulfate 2 minus, and form a kind of the insoluble materials or solid or precipitate. Here is silver sulfate. Okay, so next one will be the acid base reaction. Okay, at this moment you still only have the arenate acid base theories and move into the Bronsted acid base theories. Okay, so the definition of acid and base according to 2 theories is, for the arenate acid, this one can produce protons in the solution. Okay, so almost of the acid contain protons like HCl, like H2SO4. They can be considered as arenate acid. Okay, the guy the base according to arenes is some guy can produce hydroxide ion in the solution. So with the definition of arenate for base, only the compound contain OH can be considered as the base. Okay, of course, like sodium OH, potassium OH, like calcium OH, something like that. Okay, but in the case of arenate, there are some other things can show properties of base, like NH3. Okay, but according to arenate, NH3 cannot be considered as the NH, as the base. Okay, so let's move to the Bronsted. Let's move to the Bronsted theories. Bronsted theories say that acid Bronsted is a guy can donate protons. Okay, or in other words, is still the produce the protons. Okay, and in another side, Bronsted base is a guy can accept protons. Okay, so now they lead you to think that, okay, all of them, like the guy produce OH in solution, they can accept protons. Okay, OH minus plus H plus. Okay, we form water. Okay, and it's also say that NH3 and protons will form NH4 plus. Okay, so this one is a little bit wider than arenate, and with Bronsted you can say NH3 is the kind of the base. Okay, so from it, after the definition of acid and base, now you have another definition related to a salt. Okay, a salt is quite similar to the acid and base, but if you have a cations in that compound, if you have a cation, not is not a proton anymore, okay, but it's another cations, sodium, potassium, calcium, or iron, cobalt, something like that, okay, and anion other than hydroxide ion, it's not OH anymore, okay, or oxide, or O2 minus anymore. So the other anion like chloride minus, like bromide minus, like sulfate, okay, like nitrate. Okay, in that case, you have a salt. Okay, it's very it's common or it's familiar to you from high school as well. So, so in terms of the acid and base and also salt in this part, only according to Arrhenius and Bronsted. Okay, so we can see some of the strong acid, strong base, weak acid, weak base, of course. Okay, so there are some common strong acids as you see in the list here. Okay, it can be sodium, it can be hydrochloric acid, hydrobromic acid, okay, or hydroiodic acid. Okay, the other very common to you is this one, is sulfuric acid. Okay, so when this one can be considered a strong acid, it also means this guy is strong electrolyte and it's dissolved in water from 100% ions. Okay, so when you dip them or when you dissolve them into the water, the guy here, for example, hydrochloric acid, we form this one. Okay, we form this one, chloride minus and protons. Okay, this one produce bromide ions and protons, iodine ions and protons, something like that. Okay, and let's consider, let's help me to remember, strong acid is strong electrolyte and they form totally ions. Okay, in another side, not only strong acid can be considered as the in terms of Arrhenius and Bronsted. Okay, you also have some weak acid in that case. Okay, so for example, hydrofluoric acid, acetic acid, or carbonic acid, or sulfite, sulfurous acid. Okay, it's not sulfate, it's sulfur acid. Okay, something like that. Or cyanic acid, it's very toxic. Okay, so similar to the first one, this guy can produce an ion in the solvents or in the aqueous environments, but of course this one is not very strong one. Okay, but of course I mean this one is not cannot separate 100% into the ions. So in that solution of weak acid, you will see all of them, including acid like HF. Okay, you will see some HF molecule in that solution. You will see also some F minus. You see also proton there. Okay, similar to the acid will be the strong base. From the base at the group alkaline and alkaline earth 1A and 2A. Okay, the kind of the metals, when they meet a compounds or meet a base with hydroxide ions, okay, lithium hydroxide, sodium hydroxide, or calcium hydroxide, strontium hydroxide, like that. Okay, this one can be considered a strong base, and they are separate mostly 100%, especially for the group 1A. Okay, for the group 2A, is separate, it can be considered a strong base as well, but some of them is not really dissolved very well water. Okay. So for the other, because of UC, group 1A, group 2A, there are some metal, okay, and they can generate strong base. What about the other metals? When you have some other metals, okay, especially for the case of transition metals, okay, normally transition metal, when they form a compound with hydroxide ions, okay, for example, copper hydroxide, zinc hydroxide, or iron hydroxide, okay, this one is insoluble in water. Okay, it means that the kind of compound can be considered as base sometimes, but they cannot produce OH in a solution according to Arrhenius. Okay, and it cannot accept protons like the Bronsted said. Okay, and the other side is a weak base. Weak base normally contain the nitrogens atom in the molecule, okay, and we call that functionality in organic compounds is amine. Okay. So weak base, the most common weak base you see is ammonia, NH3, and if you change NH3, oops, sorry, I will write it here, NH3, if you change 1H or 2H or sometimes 3H by hydrocarbons like CH3, NH2, okay, CH3 2 times NH, something like that, okay. So we will have a closely related and containing compounds, or we call the derivative of the NH3, and this one can be considered, and this one is normally named an amine, okay. So this one will be considered as a weak base. And then when you dip them or dissolve them in the aqueous solution, okay, or water, you will have a process in which NH3 will take protons from water, okay, and form an ammonium ions, and of course it's release OH minus, okay. So we consider them as weak base. So this one is the summarize to you about the electrolytic behaviors of the common compounds, okay. The compounds. So the next one is neutralization reactions. Neutralization reaction is a process in which the acid and base react together and form water, okay, and a salt, right? So normally when an acid and base react together, the presence of the proton in terms of acid and a kind of the proton acceptor in base, okay, will form how to say a neutralized compounds, normally neutralized compounds, and it's water. Okay, so the other ions generated by the other part of acid and base will help you to form salt. Okay, very simple from high school. So this example is a process in which you dissolve some of the precipitate like magnesium sulfate, magnesium hydroxide by the stronger acid, okay? So you have a base, insoluble base, right? React with an acid, and now you form water and a soluble materials, okay? A soluble molecule, substance. So by that way, you will form a transparent solution, as you see here, okay? From a blind solution, blind system, sorry, and then you will get a transparent solution. So, okay, similar to the formation of water, I could say it's the low reactivity materials. Okay, if you can form some other process, some other thing like a gas. Okay, if the reaction between the acid and base form a gas like this, H2S. Okay, like the process making CO2. So this reaction, this reaction can be write as a real reactions, okay, in which you can write down the molecular equation and net atomic equation too. Okay, very simple in the case of an acid like HCl and a salt like a sulfate. Okay, now you see, even we say this reaction happened between an acid and a salt, but actually we can consider this one is a reaction between a guy can donate protons and another guy can accept protons. Okay, so this one can be considered as an acid base reaction too. So by that, when the acid base reaction form a gas, this reaction can happen. Okay, similar to the next examples. So okay, let's see about the oxidation reduction reaction. Okay, so if in the next semester, if you if you participate in the practical chemistry class, you will be introduced about the experiment in which the oxidation reaction happen. Okay, even you have time to prepare a kind of the small battery, something like that. Okay, so in the oxidation reduction reactions, the example is you adding some iron into a copper sulfate solution, and with time you will see the colors of the copper sulfate become lighter, and also you see the colors of the iron rod it change. Okay, so this one can be explained by the copper, a part of copper in the solution after the reaction, they deposit on the surface of the iron rod. Okay, so this reaction can be write down iron copper sulfate become iron sulfate and copper, and then the net anionic equation is something like that, in which irons react with copper 2 plus and form iron 2 plus and copper. Okay, so now you see the iron charge is moving from copper to irons. Okay, it means now there are a process of transferring electrons. Okay, in which irons will transfer electron to copper 2 plus. Okay, and then when iron move electron out, this means that they will become iron 2 plus, and when the copper 2 plus, they are lacking 2 electrons, they get 2 electrons from irons, they will become copper 0. Okay. So to explain about the redox reaction, we need to understand about the oxidation numbers. Okay, the oxidation numbers is considered as a kind of hypothetical charge assigned to the atom, assume that the electrons are completely held by one atom or the other. Okay, this means that it means that you have A, B, right? And now you will consider the atom stay on one of them. Okay, all the electrons belong to one of them. Okay. So to assigning oxidation numbers in the tutorial class, I say to you that there are some of the rule. Okay, to assign the oxidation numbers, like the elements. Okay, the elements, they have the oxidation number of 0. Okay, monoatomic ions, like the case of potassium, sodium. Okay, they are plus 1 plus. Okay, the numbers, the oxidation number, the highest oxidation number can be equal to the numbers of the group on the periodic tables. Okay. So for the metal, normally metal will show a positive oxidation numbers. Okay, in the reverse side, non-metal will show a negative oxidation numbers. Like the case of oxygen is -2, chloride, fluoride is -1, something like that. Okay. And the last rule for assigning oxidation numbers is the sum of oxidation numbers equal to the overall charge. Okay, so it means that with a molecule, with a molecule with normal charge, with the neutral charge, sorry, with neutral charge, this one will become 0, or the sum of all the oxidation numbers inside that molecule is 0. Okay. Normally we will use the charge of some elements like hydrogen is +1, oxygen is -2 to calculate the oxidation numbers. Okay. So for examples, we know that oxygen is a -2. Okay, so the sulfur here, the SO2 or sulfur dioxide molecule is a neutral molecule. So sulfur should have the oxidation number of +4. Okay, for the case, I will skip this one, very simple. For the case of the chloride OH, or sorry, chloride ion, sorry. Okay, it's chloride ions. Now you will see the oxidation number of oxygen is -2. Okay, so you have 2 oxygens, it's -4, and also you have one more charge. Okay, you have the charge of chloride, or the oxidation number of chloride. Let's consider as X plus -4. Okay, plus minus. Okay, equal to or equal to minus, sorry. Okay, so by that way you can calculate X equal to +3, and this one is +3. Okay, of the oxidation number. So for the case of redox reaction, you will have some process. Okay, some process we call the oxidation process and reduction process. Okay, the oxidation process is happen when a substance lose electrons. Okay, as I said to you, the electrons move from the iron to the copper 2+. Okay, so iron donate 2 electrons out or lose 2 electrons. Okay, so irons become iron 2+, and we call that process is oxidation. Okay, and be careful that substance involved in the oxidation is reducing agent. Okay, reduction agents. In the reverse side, the reduction process is happen when a substance gain electrons. So copper 2+ is get 2 electrons from irons and form copper 0. Okay, this process is namely reduction. Okay, and the guy is copper 2+ involved in the reduction process will be named oxidizing agent. Okay, be careful because of the oxidation is a process and reducing agent is the substance involved. in that process. Okay, it's a little bit different, and I hope you will not be too confused about that. Okay, so in another side, you can see in the oxidation process, the oxidation numbers will increase. Okay, increase of oxidation numbers. And in the other side, the reduction involved with the decrease of oxidation number. It's okay. So this one is a summary to you is the oxidizing process of the oxidizing agent and reducing agents. Okay. So the reaction in the part you see in the examples you see when we do dip an iron rod into the copper solution is named displacement reaction. Okay, and this one can be explained by an active or described by an active metals. We replace or displace a metal ion from a solution. Okay, this look like the active metal will replace the position of the less active metal from solution. Okay, you know, in the activity series from high school, right? You have some sentence to remember that. This look quite easy at this moment, right? So magnesium is the higher reactivity than copper. Okay, so when you put the magnesium solid into the solution of copper chloride, the magnesium will replace the position of copper in the salt, and you get this new salt, magnesium chloride. Okay, and of course, because of copper now is pushed out from the salt, they will appear as the copper solid. Okay, so the activity series is the show like that, and you know it's from high school, I'm sure, with a very famous sentence. Maybe you studied from the 8th grade or 9th grade. Okay, so let's keep it. So this reaction is some similar thing in which you dip the copper into the silver solution. Okay, and when you see in the periodic in the activity series copper here and stay higher than silver, this means that copper is more reactive. Okay, it's higher reactivities than silvers, so copper can push silver out of the salt, or we can say copper can donate electron to silver plus. Okay, and it's form a copper 2 plus. Now it stay in solution, and silver as the solid, as you see, is the silver appear on the outer of the copper, okay, of the coppers, and the solution from transparent, from the colorless to become a little bit blue. Okay, because of the presence of some copper. Okay, so with this one, I can give you another example. A video. Okay, I will give you a videos of the process we are recording in the laboratories, in our laboratories. Okay, so let's see the growing of the silver when we dip a copper rod in the solution of the silver nitrate. Okay, so you see this one is the copper, this one is the silver crystals growing. It looks like a tree, right? So in the process of silver of the copper takes the place or the redox reaction between copper and silver nitrate. Now you see the copper will be dissolved in some part around here, okay, in the base, and then the electrons will move from the base, from the position in which copper dissolve to the border, or to the side, to the surface, sorry, to the surface of the silver crystal, and then they react, the reaction between silver plus and electrons will have to appear on the surface, and a new silver will be deposited. So you see it's growing. Okay. Okay, it's okay, never mind. Okay, so now you see the redox reactions is happen, something like that. The redox reaction, actually, they can be separated into two types. The first one can be considered as the redox, the normal redox reactions. Okay, and the second type can be considered as the electrochemical reactions. Okay, in which the electron can transfer inside the metal, for example, like you see in the videos, in which the electrons will move from the surface of the copper when the copper moves to copper 2 plus and dissolve, and then they transfer to the surface of the silver crystal, and then the reaction between the electrons and silver plus to form a new silver is will appear on the surface of the silver crystal, not the position in which copper dissolve. Okay. Second, please. So let's use the activity series. When we use the activity series, this can help you to answer this question very simple, right? You have two substances, iron chloride and magnesium. Will they react together? Of course, yes, because the magnesium is more reactive than irons. Okay, let's open the activity series, and then you will get you will get the answer. Very simple. It's okay. So based on the beside the classification of chemical reaction based on the acid-base reactions and redox reactions, okay, we also can classify them in some other way. Okay, in this part we separate them based on what we see in the products. Okay, what we see in the products. There are four categories of the reactions in this kind of classification. Okay, in the first one, what happened? In the first one, we call this kind of the reaction is the synthesis reactions or combination reactions. Okay, in which you start from 2, 3, or more compounds, and you generate one compound. Okay, this one can be considered as the combination reactions. Okay, this one can be also considered if we say the products, okay, the number of products is less than the number of reactants, something like that. Okay, the other kind is a decomposition reaction, in which you start with one reactant, okay, and in the products you produce 1, 2, 3, 4, 5, or many other molecules, okay, many other products. So this one is decomposition reactions. The displacement reactions is exactly the reaction you see in the redox reaction between copper and silver nitrate, as on the videos, okay, or a lot of example before. Is the one metal or one active metal will take a place of the less active metal in the salt, okay. And the last type is double displacement reactions. Okay, as you see, you can imagine this a reaction between an acid and base. Okay, between an acid and base to form a salt and water. Okay, this one is can be considered as the double displacement reaction. Okay. So for more detail, the combination reaction is the guy of the simple substances we react together to combine together and form the more complicated substances. Okay, like this one, sodium react with chloride to form sodium chloride. Very beautiful. Okay, or the reaction between calcium with the carbonic acid, with the carbonic gases, and form calcium carbonate. Okay, so the reaction of them or the example of them is very simple, and you can find it anyway. Just help me to imagine if you start with 2-3 compounds, okay, 2-3 simple substance, and when you form a more complicated or more complex substance, this one is combination reactions. The reverse reaction of combination is decomposition. Okay, if you start with a complex substance and this one react or decompose to form more simple or simpler substances, of course the number of substance of the product is higher than the reactants. Now you have a decomposition reaction. Okay, the displacement is what I said to you before. An element displace another in compounds, and double displacement is exactly the reaction between acid and base, for example this one. Okay. Okay, one type of the reaction is the lattice here. Actually it's a kind of combination reaction, but we let it how to say individual because of it's too famous in high school, and it's also very famous in the real life. Okay, you can see it's very familiar in real life, I could say. So the combustion reaction actually is a reaction of substance with oxygens. Okay, and normally this one will release some heat, sometimes produce flame. Okay, it sometimes produce light. Okay, so of course when a substance, okay, when a substance react with oxygens, normally they will produce an oxide. Okay, like an example here, iron with oxygen become iron oxide. Very simple. Or some other reaction, let's take this one, the pyrite. Okay, react with oxygen to form. Oh, I don't know what's happened with my pens. Okay. Okay, something like that. It can produce one or more oxide. Okay, so in these reactions, this one is combination reactions. Okay, a kind of combination reaction is also a kind of redox reactions, in which you see the iron here is an element. Okay, the oxidation numbers is 0. Oxygen is an element too, and the oxidation number is 0 too. Okay, after the reactions, the oxygen become -2 and the iron become +3. Okay, this one is the oxidation reaction, redox reaction as well. So, okay, so let's move to the next introduction into the how you can work with a solution. Okay, actually this one is the is very simple thing. Maybe you understand, you know from high school as well. Of course, not as well, I'm sure. So the first type you need to make familiar is molar concentration. Okay, and the second one is process diluting solution. Okay, or so why this one stay here? This lectures, I think, is quite a new lectures from form because of we found in the laboratories many students cannot calculate the molar concentration firstly, and secondly they cannot prepare the right concentration solution. Okay, so hope that after this one, at least after this one, you have some very first knowledge on the working with the solution in laboratories, because in laboratory in most times we only calculate the molar concentration, and which only need to know how to prepare the solution with right concentration, just it. Okay, in the laboratory you don't have to burn anything to calculate the components inside. Okay, the main work in laboratory is calculate the concentration, the molar concentration, and prepare the solution with dry concentration. That's it. Okay. So this one is introduced before the solution, including solute, solvents. Okay, and of course the solute need to be dissolved or solute in the solvents. Okay. Okay, so there are two things. Let's help me to remember the concentration. Okay, normally concentration will be defined as a given the quantity of the solute in a given volume of solution. Okay, normally it's a 1 liter. So the concentration here will have a unit of gram per liter. Okay, and this guy can be calculated very simple with the mass of solute. The mass of solute calculated by gram over the volume of the solution. Okay. The second type of concentration is normally used is molarity. Okay, from this moment is the molarity. You also have some other type of the concentration, okay, like percent concentration or percentage concentration, like molarity concentration, something like that. But with my experience in more than 10 years working in laboratories, I never use molarity concentration. I use only molarity concentration, and sometimes the concentration with gram per liter, as you see here. Okay, this one and this one. The other concentration is the very rarely used. Okay, so just understand, help me to understand the concentration of mass of solute on the volume of solution. You see, it's a normal concentration. And the other type is molarity, is calculated by the numbers of mole of solute. Sorry, guys. Don't worry, COVID, I'm not in COVID situation, and the COVID cannot move through the internet, right? So the molarity is calculated by the number of mole of solute in a volume of the solution. Okay. is the mole of solute over the volume of solution. Okay. So to calculate the molarity, you should know the mole of the solute, mole numbers of the solute, and you should know the volume of the solution. Just it. So you have the relationship between molarity and concentration by the molar mass. Okay, the molarity, when you multiply to the molar mass of the solute, you get the concentration gram per liter. Okay, if you divide to molar mass, you will get the mole per liter. Okay, so in a very simple way to understand is the molarity normally can be write as concentration Cm, right? Multiply to the molar mass M, right? The Cm is calculated by the mole numbers N over volume multiplied to the M, the molar mass. So when the mole number multiplied to the molar mass, you will get M, or mass of the solute over volume, and this one will become concentration. Okay. So to prepare a solution by the diluting method is a process you prepare a solution by adding some water there. Okay. Okay. So the concentrate solution, a high concentrate solution, after you add water there, it's become diluted solution or low concentration or low molarity. Okay. So the main idea to prepare a right solution by diluting method is, let's understand the mole of the solute before dilution equal to the mole after dilution. Okay, the mole numbers, okay, Cm, or the molarity calculated by mole number over volume. Okay, sometimes this one is right at M, like from right here. Okay, normally M is writing for the molar mass. So let's understand M is Cm. Okay, it's no problem. So is this one, you will have M multiplied to V equal to N. Okay, equal to the mole numbers, and mole number is not change. So in two solutions, you will have the concentration multiplied to the volume of the first one. Okay, equal to the concentration multiplied to the volume of the second one. So it's the main idea for you to calculate it. So if you need a new solution, M2, okay, you have the solution of stock is the concentration of M1. You only have to do like that. M2 will equal to M1 multiplied to V1 over V2. Okay, or if you see you have the concentration of the first solution of second solution, and you have to calculate the volume of the second solution, let's do the same thing. V2 equal to M1 V1 over M2. It's okay, very simple. Okay, so after you know V1 and V2, this means that you have to add the amount of water equal to V2 minus V1. Just it. Very simple. Okay. Okay. So I will skip this because of we have to move to the a little bit in several next slide. So now it's 9:26. Can we go for 10 minutes more, guys? I think yes. Okay.
Yeah.
Thank you very much. So let's take these examples, this exercise, and let it for your homework. Okay. No, Phong, he give the he give the solution here. So when you dissolve a compound into the solution, okay, in solvent to get the solution, as the ionic compounds, as strong electrolyte, for example, okay, the solute ionic compound will dissolve or dissociate completely in the solution. Okay, so it means that you have a AlCl3, for example, dissolve in the solution and form aluminum 3 plus and 3Cl minus. Okay, so let's consider what is the solution stoichiometry. Stoichiometry is the ratio of the component inside the molecule. Okay, for examples, in this one, stoichiometry between aluminum and chloride is 1:3. Okay. Ooh. Sorry, guys. The class is finished at 9:15.
No, it's 10:50, 15.
10:15.
Yeah.
Because of Phong, yesterday Phong said to me that your class is from 7:30 to 9:30, so it's the reason why I go very fast.
Because the schedule have changed these 2 weeks. We have extended the class, I think, because on Moodle, last week and this week is to 10:15.
Okay. I don't know that because Phong just said to me that he busy today from yesterday, and he sent me the slide, and he said that your class is in around 2 hours from 7:30 to 9:30. So it's look good. No, so we can continue, of course. So after I finish, okay, actually it's almost finished, I think. And after I finish, if we feel something we need to make more clear, okay, let's go back. So I thought that I talk too much and too fast, but I still cannot finish this lectures on time. But actually, the lecture is is longer than I think. So, okay, so let's continue to the stoichiometry. Okay, the stoichiometry is the ratio of the component inside the molecule. Okay, for example, in the molecules of aluminum chloride, you have one aluminum, okay, combined with 3 chloride. Okay, so the stoichiometry of them is 1:3. Okay, so let's consider the concentration, okay, of aluminum in the solution is 1 mole per liter. Okay, so the stoichiometry ratio 1:3 will give you the information that the concentration of aluminum 3 plus is 1 mole per liter 2. And the concentration of the chloride minus is 3 mole per liter. Okay, so is the solution stoichiometry. So by that way, by that way, you can calculate the concentration of O species in the solution. Okay, so when you dissolve the solution, the magnesium chloride in the solution, this one is completely dissociate into the magnesium 2 plus and 2 chloride minus. Okay, so if we start with 0.25 mole per liter of the magnesium chloride, the concentration of magnesium 2 plus, okay, is the ratio of 1:2. So now you see the concentration of magnesium 2 plus will be the same with the concentration of the magnesium chloride in the given point. Okay, and the concentration of chloride become 2 times of that value. Okay. So let's go for the last part, the quantitative analysis. Okay, the quantitative analysis is the most simple technique and the first technique the student study in chemistry have to make familiar. Okay, the name of them is look quite simple, right? The gravimetric analysis is the determination of amount of substance in gram, okay, in the mass, and the volumetric analysis is the determination of the amount of substance in the material by using the volume. Okay, very simple. So for the gravimetric analysis is the process we are changing. Okay, we are changing some of the ions. Okay, some of the ions. By that we will determine, we will prepare some kind of precipitation. Okay, so from the unknown solid, and we only know that this one dissolved in a solution. Okay, we only know that this one dissolved in the water, so we dissolve them in water, okay, to form a solution. Okay, we have the first mass of that unknown solid. Okay, in the second part we will let that kind of unknown solid react with the known substance. Okay, react with the known substances, okay, to form precipitate. Okay, so in this one, at least we know one part of the precipitate. Okay, it can be a negative part, it can be the positive part. Okay, so if we use some kind of no substance like sodium sulfate, for example, okay, if you see the precipitated, now you can neglect or skip the calculation on sodium because of sodium of the cation, because of sodium of the anions, the unknown anion, because of sodium. You know that all the kind of sound of sodium is soluble, right? So we can think that, okay, that is mean that unknown solids will combine, we will include some kind of cation that can precipitate with sodium, with the sulfate ions, something like that. Okay, so do several kind of the reaction with known substance to define what kind of the precipitation is appear. Okay, of course we need to know the excess amount of known substance. Okay, the excess amount is here to increase the precipitation reaction to highest yield as possible. Okay, and after that we weight the precipitate. Okay, to define the percent of iron in unknown solid And from that, we can compare them with the theoretical calculation. Okay. And from that, we can define the solid, the unknown solid. Okay. So the explanation or description of the process of the gravimetric analysis. Okay. In terms of the experiments, you see, normally you will put some kind of the known material, okay, to the unknown, and by that you prepare some precipitate. After the precipitate appear, we will filter the precipitate, dry them, and weight them. Okay, and then you calculate the mass, the percent of each component in unknown, and compare to the theoretical calculation, and then you can define them. Okay, the how to say, the practical chem subjects on the next semester of you will start with this exercise, I think, with this experiments, I think. Okay, in another kind of the technique to define the material is a volumetric analysis. Okay, the volumetric analysis is the method to determine the amount of particular substance, okay, based on the measuring of the volumes of the solution. Okay, so the technique for the volumetric analysis is namely titration. Okay, so the titration is a process, actually is help you to determine an amount of one substance by a reaction with another substance. Okay, and when we do the titration, we will carefully measure the volume of the known substance B. Okay, when we measure that and we stop the reaction at the position or at the point the reaction between A and B just complete. Okay, it's look like that. For example, you do the reaction of the HCl. Okay, oh sorry, no, it's not HCl here. You see HCl here. HCl. Okay, in this you have a NaOH, for example. Okay, this one will contain some drop of the phenolphthalein. Okay, the phenolphthalein is this one, is the indicators. Okay, so when you use the burette to continuously, slowly drop the sodium hydroxide into the hydrochloric acid. Okay, so when you move them drop by drop, the reaction between the sodium hydroxide and hydrochloric acid will happen, okay, immediately. Okay, in the very first point, the pH of the solution here is an acidic solution, right? So the pH is lower than 7. Okay, so when the sodium hydroxide react with the acid hydrochloric, okay, the concentration of proton reduce and the pH will increase. Okay, and the pH increase. So when the pH, when the hydrochloric acid react completely with the sodium hydroxide, the next drop of the sodium hydroxide will let the solution move from the acidic solution to the alkaline solution. And when the alkaline environments with pH bigger than 7 appear, okay, the phenolphthalein will be how to say, will react and it turn to become pink, okay, to become pink colors. So we will stop the reaction at the point, the solution just turn to pink. Okay, a very faint pink color we reach. We stop there. So by that we can calculate exactly an amount of the sodium